we've solved a number of problems involving multiple forces where there's been something that we call an internal force. That's a force that's acting between two objects within the system. But up until now, we've ignored everything that's inside the system. Remember the analogy with the ice cream truck, right? When the ice cream pallets bumped against the side of the trucks, we didn't pay any attention to the force that acts between the ice cream pallet and the side of the truck because it didn't contribute to the motion. But there may be times, there will be times when the internal forces are important. Okay, if I'm an engineer that's designing some kind of system like a train, let's say, the external forces are clearly important to me. The force of friction acting on the train, the force that the train engine can pull with. But there's also internal forces that are important as well, like the force between the 37th car and the 38th car, the coupling. I need to make sure that I design that coupling strong enough to hold it. So, in addition to being able to analyze the motion of the train itself, paying attention to only the external forces, I do have to have a way of analyzing the internal forces, the coupling in the train, the force between the ice cream pallet and the side of the truck. So, we have a situation where we have maybe a couple objects, and one object is being pulled to the right, we'll call it F2. Another object is being pulled to the left, we'll call it F1. Up until now, we've just treated this like one object 1 and object 2, we've combined their masses and then just said F net is equal to F1 plus F2. But today what we're going to do is learn to find what the force is that acts between those two objects. This force of tension in the rope that joins them, or we could say the force of the coupling in the train, or we could say it's the force of the ice cream pallet acting on the side of the truck. Whatever the case may be, the internal force. But the good news is, although it's more work than analyzing just the system, the good news is it starts off exactly the same way. We have to find the acceleration of the system first. So regardless of what's going on inside this system of these two masses, it doesn't matter right away. It matters later on, but not right away. Okay, when we're analyzing this system, what I want to do first is find the acceleration of the system. Let's do the entire system as before. So pretend that we've got one object right here that has a mass of 25 kilograms. And we know what to do with that, right? We say F net is equal to the sum of the forces. We're going to say, I'm going to call this FF1 and FF2. I've got the force of friction on the 10 listed separate from the force of friction on the 15. Bottom line is, both of those force of frictions are external forces that contribute to the motion of this system. So we're going to say F net is equal to FF1 plus FF2 plus the force applied, which is 50 newtons. Okay, no difference so far. If I had asked you to solve this question last week, at least the acceleration of this system last week, you would have done it exactly the same way as we're doing it right now. Nothing's changed there. Now the net force is m times a. That's 25 kilograms times the acceleration. FF1 is negative 20, FF2 is negative 25, and FA is 50. So again, nothing's changed yet. It's coming, but nothing's changed yet. We have to first get the acceleration of the system by doing what we've done many times before. 25 times a is equal to, that looks like 5 on the right-hand side. And a will therefore be equal to 5 over 25, or 0.20 meters per second squared. So far, it's exactly the same as what we did last week. Just treat it as a system. But when you're looking for that internal force, that force of tension in the rope that joins the two masses together, or that coupling force that joins the two train cars together, now we have to analyze an individual object within the system. Now, it doesn't really matter which one. Pick the 10 or the 15 and go with it. I'm going to pick the 10. On the 10 kilogram object, on just the 10 kilogram object, there is FF1 acting to the left. Anything else? besides gravity and normal force that cancel, something's got to be pulling on FF1, or sorry, on the 10 kilogram object. Otherwise, this thing isn't going to move with the 15 kilogram object. The rope, I'm going to call that FR, the force of the rope, or better yet, we're looking for the force of tension, we call it. So let's call it FT. The force of tension acting to the right. That's what I'm looking for, right? Notice I've ignored the 15 kilogram object. I'm looking at all of the forces acting on one object now, and then I'm going to do an F net with that. So I'm going to say F net is equal to F1. That's the force of friction acting on the 10 plus the force of tension acting on the 10. I'm not going to include the 50. How come? Yep. Good. It's not directly on the 10. It's acting on the system, and if you were analyzing the 15, it would be acting directly on the 15. Okay, but it's not acting directly on the 10. Same with the force of friction 2. It's acting directly on the 15, and we can consider that to be on the system as well, but it's not acting directly on the 10 kilogram object. Question? Okay. So F net, we're going to say this time is what? M times A? M is, what's my mass here? 10. Yeah, we're analyzing, like, forget about the system now. We're analyzing the one object. 10 times A is equal to FF1, which is negative 20, plus the tension, which is what we're looking for. Oh, I got two unknowns, right? Wait, no, I don't. What do I have that I haven't put in here? I got the acceleration. Look, if the system is accelerating at 0.2, then so is mass 1 accelerating at 0.2. So 10 times 0.2 is 2. I'm going to take the negative 20 over to the left-hand side by adding, and I get the force of tension here is 22 newtons. So I treated it as a system like I did last week. I got the acceleration of the system, and then I used that acceleration of the system to analyze one object that had the tension acting on it, and then I solved for the force of tension. Now, what do you think would have happened? I told you guys you could pick whichever object you want to analyze in part B. What do you think would have happened if I had analyzed the 15 kilogram object? What do you think I would have gotten? What do you think the tension would have worked out to be if I had analyzed the 15? The same? If object A applies a force on object B, then object B, finish my sentence. Braden says, thinks we would have gotten negative 22. We're going to do a quick little check of that. If we analyze the 15 kilogram object, we have an applied force to the right. That applied force was 50 newtons. We have a force of friction to the left, and that was, we'll call that FF2, and it was 25 newtons. And then we have a force of tension to the left as well, because object number 1 is pulling back on object number 2. So this is a little bit harder to analyze object number 2 because there's 3 forces versus 2 forces. But I shouldn't really say harder, just a tiny bit more work because there's more numbers in here. We're going to say F net is equal to the sum of the forces. F net is equal to Ft plus FF2 plus Fa. The total mass here is 15 times 0.2 equals the tension, that's what I'm looking for, plus negative 25 plus positive 50. We get 25 on the right-hand side. 25 goes over by subtracting. 15 times 0.2 is 3. 3 minus 25 gives me, go figure, just as Braden said, Ft will be negative 22 newtons. So if I give you this question on a quiz or test to say, find the tension of the rope that joins the two together, find the acceleration of the system, and then analyze one object or the other. If you analyze the one object, you get positive 22. You analyze the other one, you get negative 22. I can live with either answer, positive or negative 22. If you have time, do it both ways. If you do it both ways and you get the same answer, What are you pretty confident in? I mean, you got to be sure you're right, right? Like the odds of you getting the same answer but wrong are virtually non-existent. So if you get the same answer, like you've got to be right. Yeah?
Why is there 3 forces on that one but only 2 on the other?
Why are there 3 forces on that one and only 2 on the other one? Well, if we look at the 10-kilogram object, friction is, like, I think we can agree that friction is acting on the 10-kilogram object because there's 2 surfaces in contact. Now, look at the 15. There's also friction acting on it, but it's a bigger force because it's a bigger mass. So there's a force of friction of 25 newtons acting on this. So friction acts on both of them, right? Well, the 10-kilogram object isn't, like, it's not going to be going anywhere if the rope isn't pulling on it, right? So I pull on the 15, and then the 15 pulls on the 10 with the rope. So there's got to be a force of tension there as well. Those are the only 2 forces that act on the on the back object. But if that rope pulls on the 10, then it has to pull back on the 15 as well. So the tension has to act on the 15 as well. So now we've got 2 forces acting on both, friction and tension acting on both objects. Now the thing that separates the first object from the second object is that object number 2 here, this 15-kilogram object, also is being pulled by a force of 50 newtons. So I pull on the 15 with a force of 50. Tension pulls back with a force of 22, and friction pulls back with a force of 25. Whereas when I look at the 10-kilogram object, yeah, I'm pulling on the 15 with 50, but it's only the tension in the rope that's pulling directly on the 10-kilogram object, not this 50-kilogram or 50-newton applied force. Does that work? Okay. Yep. You would call it whatever you want, right? Like we say when we're naming other forces, like if you want to call it, I call that FF1 and FF2 just to keep them separate. You should call them 2 separate things, but if you just want to call it F1 and F2 or whatever the case may be, it doesn't really matter as long as you've named them something different. Okay? So your strategy is do the system, do what we've done, and then pick an object and analyze just that object. All right, I'm going to give you a question to work on here, and that's what we're going to leave it off with here today. We want to find the force of tension in the rope joined in the 2 boxes. Again, this force in between. I'm not going to guide you through this, but I will give you a quick little reminder, a quick little heads up. You first want to analyze the system, and then after you analyze the system, you want to analyze one individual object.